So for this definition, for this integral, I'm gonna derive the result. I'm gonna do the proof rather. So let me start by writing the integral, of course. So that is the integral from 0 to infinity of x to the m e to the a negative ax to the n power dx. But we need to do a use substitution. So let's make let's make the substitution t equals to a x to the n power. That means x to the n power equals to t divided by a. All right. And what else? And furthermore, x equals to t to the 1 over n over a to the 1 over n. All right. So let me do this 1 over n like that. All right. Okay, so if we find the dx right here, dx will be the derivative that is 1 over n times t to the 1 over n minus 1, all right, divided by the quantity a to the 1 over n dt, right? We're just using the general power rule for this. Let me actually write this 1 over n even better so you can easily see what happened here, all right? Okay. So I'm going to solve for dx right here, okay? So dx, oh no, actually I have the dx. Oh no, actually let me simplify things a little bit. dx, more compact, t to the 1 over n minus 1 over n a to the 1 over n dt, all right? So this is going to be our substitution. So let's go back to the integral here. Okay, so and again, the limits of integration will be the same 0 to infinity because for t, okay, for x equals to 0, 0 to the n is 0 times a, that's still lower limit of 0. Upper limit, infinity to the n, it's still infinity. Infinity times a, that's still positive infinity. What we're going to do here, remember this x right here will be replaced over here where we see the x, okay? So yeah, so that means t to the 1 over n over a to the 1 over n raised to the m power. And what about e to the over here? Let me use a different color to highlight. This is going to be our t, right? E to the negative t, okay? And what about the dx? Dx will be all this madness here, all right? Which is t to the 1 over n minus 1 divided by n a to the 1 over n dt. Okay. Well, let's actually do some simplifications. Okay, so do you guys agree this is the integral from 0 to infinity t to the m over n over a to the m over n e to the negative t, and maybe I should make more room over here. Okay. And times the differential t to the 1 over n minus 1 over, what is that? N a to the 1 over n dt. All right. So yeah, it looks like a lot of crazy powers and like a lot going on. So check this out. Let me change colors to highlight. So T's with T's on the one hand. And on the other hand, how about uh, A's with A's? Okay. So the T's in the numerator, well, actually, let me talk about the A's. So, do you guys agree that A in this case is constant? And do you also agree that we have the same power, the same base, A? What do we do with the power m over n and 1 over n? Do we add them together? Okay, so this will be equal to 1 over, and actually this n can go outside. A to the m over n plus 1 over n, okay? And that's times the integral from 0 to infinity of, what about the t's? I'm going to combine t over t to the rather m over n, which is this power, and add it with plus. I mean, this is m, 1 over n minus 1 dt, I mean e to the negative t dt. The rest of the problem is just combining fractions together. I mean, look at the exponent here. This is n a to the m plus 1 over n, 1 over that, integral of, combine these two together, what is this? M over n, 1 over n, and we'll leave this negative 1 over there. Check this out. T to the m plus 1 over n minus 1, all right? E to the negative t dt. And guys, this is where we see this, what's it called, the gamma function. Because, back to the gamma function, back to the definition of the gamma function, we have n minus 1. Well, the n looks fancier, looks like a crazy fraction. So this is going to be, this guy will be equal to, all this integral means the gamma of m plus 1 over n divided by n a to the m plus 1 over n. That's actually a power, right? And this is n. And that's the end of the result. All right, but I mean, what we care about is how we're going to use this integral, all right? We're going to, or rather, this formula. So let's see about it. Let's see about some exercises on the next page. So evaluate the integral from 0 to infinity of x to the 7 e to the negative 3x squared. All right. No, guys, you don't want to do integration by parts. I don't think it's going to be a fun problem. Instead, all we're going to do is identify three parameters. M, okay? So let me identify M, which is the power of x, that equals 7. A, which is whatever multiplies the exponential without the negative sign, that is just 3. And N, which is the power of x, in this case, which is 2. That's all you need. All you need to do is substitute into that gamma function formula. Okay, so this will be, okay, gamma, I'm going to write the formula only once, so that's gamma of m plus 1, no, m plus 1 over n divided by n a to the m plus 1 over n, which is gamma of what's m, 7, plus 1 divided by n, which is 2, divided by n. What's n again? Is that 2? What's a? Is that times 3 to the, let me write it like this. 7 plus 1 divided by 2. All right? Just simplify this using some arithmetics. So this would be 7 plus 1 is that 8 divided by 2 is that 4. So this is gamma of 4 divided by 2 times 3 to the 4th power. But what's gamma of 4? Remember by the definition of the gamma function. So gamma of n equals n minus 1 factorial, or gamma of n plus 1 equals n factorial. Either way, I'm going to use the second version. So in this case, 1, so this is 3 factorial over, what is that, 81? 3 to the 4th power, is that 81? Times 2. And then what's 3 factorial? 3 factorial, is that equal to 6? 6 divided by 2, is that, no, that's 3 to the 4th power. No, that's not 81. Hold on. That's 162. 162. And this is 6 divided by 2, is that equal to 3 over 162? Okay. And 1 over 27. Okay. Because they're both divisible by 3. 3 equals 2 equals 8 plus 1 equals 9. That's a divisible. All right. So let's do the next one. For the next one, So that's m equals to the power of x, which is 3. A equals to 4, whatever multiplies the variable x in the exponent without the negative sign. And lastly, yes. And then before we move on to let me go back to letter A. So this is 81 times 2. I shouldn't have written this 2 anymore, right? And that is, yeah, 3 over, I mean, that's 6 over 1, 6. Oh, wait, blue. That's 6 over 162. And yeah, that's the 1 over 27, right? Okay, so let's see. Okay, so for the next example, let's do the same. Uh, we also need n equals to 8, which is the power of x in the exponent, of the exponential. All right, guys, so substituting the formula, compute, simplify. This is gamma of, what is that? M, which is 3, plus 1 divided by n, which is 8. And that divided by n, which is 8, times a, which is 4, divided, I mean, 4 raised to the 3 plus 1 over 8. Okay, so 3 plus 1, is that equal to 4? 4 divided by 8, is that 1 half? So that's gamma of 1 half divided by x, oh, no, not x, 8 times 4 to the 1 half also. All right, but what is 4 to the 1 half? Is that the square root of 4, which is 2? 2 times 8, is that a 16? So this is 1 over 16 gamma of 1 half. All right. Well, but we don't have the result for gamma of a half, but spoiler alert, it's just down here. Gamma of 1 half equals to the square root of pi. All right, guys, I'm going to show you the derivation of where or how do we get that gamma of 1 half equals to the square root of pi. Okay, so number one, uh, to show this, okay, use the definition, the integral definition of the gamma function. So gamma of 1 half equals the integral from 0 to infinity of t to the n minus 1, where this is 1 half minus 1, e to the negative t dt. Okay. Well, simplifying this, we get, okay, the integral from 0 to infinity of t to the negative 1 half e to the negative t dt, which, even better, this is even more simplified. This is the integral from 0 to infinity of e to the negative t divided by root of t dt. All right? How do we evaluate this integral? So, well, I'm just going to give you the substitution, whatever, which is what actually works for this substitution. So, let's set u equals to, or rather, no, not u, actually t equals to u squared. I know that substitution just came out of nowhere, but actually this is what we will do to make it work. All right. Well, so dt, okay, dt equals to 2u du, which means, what is that? Which means u also from here, u equals the square root of t. All right. So we're going to use to rewrite that integral. Okay. So this will be, after the substitution, that's the integral. Okay, what is e to the negative t? Well, what did we say about t? U squared, sorry, e to the negative u squared divided by the square root of t. But what's the square root of t? Isn't that u? And what's dt? 2u du. What about the limits of integration? The limits of integration remain 0 to infinity, because for the lower limit at t u equals to u squared, 0 squared it's still 0, and infinity squared it's still going to be infinity. All right, well, let me simplify this integral to get the following. So this will be equal to, cancel the u's, And this equals to 2 times the integral from 0 to infinity of e to the negative u squared du. All right? Yes, at this point, it seems like we're moving on through the integral. But if you observe that integral, we're screwed in a way, right? You see why we're screwed? Because we can't evaluate this integral using u substitution. So we wish we had a u right here, but we can't multiply by u divided. Well, actually, we already canceled it out, right? So what do we do about this one? What do we do? Okay, so check the trick. Let I be simply the integral from 0 to infinity of e to the negative u, okay? Um, Squared du. All right. Okay, guys. What about it? Okay, let's square both sides of that. So let me square. Uh, so I squared equals to the integral from 0 to infinity of e to the negative u squared du quantity squared. Do you guys agree that this would be the same as the integral from 0 to infinity of e to the negative u squared du times itself, the integral from, I mean, times not equal. Oh, come on, times 0 to infinity e to the negative u squared du. All right? Do you guys agree with this? I mean, we're squaring a quantity is the product of the quantity in itself. But that doesn't seem like the problem. It seems like the problem is getting more complicated than it actually looks. All right. However, what's the trick here? I'm going to change the variables here. Instead of u, I'm going to use x or y. Okay, actually, you can do that because the dummy variable, that's just an intermediate variable, regardless of for a definite integral. It doesn't matter if your integral is in terms of u, or if your integral is in terms of y, or in terms of x, or whatever, or t. Doesn't matter. Check this out. I'm gonna write I'm gonna write this integral. Uh, well, you know what? I forgot to do something before the derivation. Okay, do you see these two? And this is actually an even function. This is the same as saying only one time the integral from negative infinity to positive infinity. So negative infinity to positive infinity, negative infinity to positive infinity, negative infinity to positive. Forgot to take that into account. All right. Forgot that. Okay. I'm back to this. So I squared, which is still I squared. I'm going to change one of the integrals from negative infinity to positive infinity to an integral in terms of x times the integral from negative infinity to positive infinity into an integral in terms of y, all right? Because again, it doesn't matter what intermediate variable do we have. In the end, we're going to get a numerical result, all right? Because now from Calc 3, whenever we have the product of two integrals where they are independent in their variables, we can write this in terms of a double integral e to the negative x squared minus y squared dy dx or dx dy. It doesn't matter. The order doesn't matter. Okay, Calc 3 people. I mean, people who already took Calc 3 people, or took Calc 3. How do we evaluate this integral?
That's something you square. Negative something you square. I forgot what it is.
What is that?
Only the y's.
The y's. Okay. Any other ideas?
Change it to something coordinates.
Something coordinates. What are those coordinates? Polar coordinates. Change these to polar coordinates. Yes. All right. Okay. So remember in polar coordinates, this would be the double integral. I'll take care of the limits in a second. Careful. All right. Do not write anything. So x squared plus y squared, remember, is that r squared? All right. But because it's negative, this is e to the negative r squared. What about the y dx in terms of coordinates? Help me out here. What is that equal to? R d r d theta, right? And we will be able to evaluate this integral here. What about the limits of integration? Hey, check. because we're going negative infinity to positive infinity in both the x and the y. Essentially, we're considering the entire Cartesian plane. And in terms of circular coordinates, we are working on an infinite circle where the radius it's still going to go between 0 and the radius will be infinity. Why not? Infinity radius. And what about the angle? 0 to 2 pi. All right, 0 to 2 pi. Okay, go for it. Let's evaluate this one. So u equals to negative r squared du equals negative 2r dr. We wish we had a negative 2. Yes, we can make our wish come true. Multiply by negative a half on the outside of the integral, right? Yes, integrating for a dream, right? So what is that equal to? So this is I squared still, all right? This is I squared equal to negative 1/2 integral from 0 to 2 pi, all right? And what is this going to be? Oh, okay, okay. So you might want to do the following, guys, because this is negative. Okay, let's integrate. Okay, this is the integral from e to the negative u. No, e to the u du d theta. The limits of integration, be careful. The lower limit at 0, 0 squared times negative 1, that's still 0. But what about infinity? Infinity squared, it's still infinity. Times negative, it's going to go to negative infinity. And this looks weird, right? The upper limit being smaller than the lower limit. But again, by properties of integrals, you can use this negative sign and reverse these limits of integration. This will be equal to 1/2 integral from 0 to 2 pi, integral from 0 to infinity, e to the u, du, d theta, and what's left? What's next? I squared equals to 1/2 integral from 0 to 2 pi of e to the u from 0 to infinity, d theta. That's 1/2 integral uh, from 0 to 2 pi. And guys, technically, I should write a limit definition, but I'm just going to go a little weird with it without the limit notation. This will be e to the 0 minus e to the... Uh, oh, actually, it's negative. What the hell is going on here? No, wait. Let me go back. Nothing to see here. From negative infinity to 0. From negative infinity to 0. Okay? Okay, this is so fine. Okay, so negative infinity. The theta, this is 0 e to the 0. Is that equal to 1? This is 1/2 integral from 0 to 2 pi. The theta, and this is still I squared, right? That's 1/2 theta from 0 to 2 pi. And I squared equals to 1/2 2 pi minus 0. And I squared equals to pi. Solving for I, what is that? Square root of pi. And this is how we get that gamma of 1/2 equals to square root of pi, right? Of course, I mean now let's use this definition of the square root of pi of gamma of 1/2 equals to the square root of pi. Okay, so now let's evaluate these other integrals right here. Okay, so two more integrals. All right. So the integral of the square root of x e to the negative square root of x. Okay, so what do we do? So m equals 1/2 n, well, a equals to 1, whatever multiplies the quantity here, that's a 1, all right? And n equals to 1/2. How? Well, that's because the integral from 0 to infinity, that's x to the 1/2, e to the negative x to the 1/2. There's an invisible 1 that will be our a, all right? Well, let's just use our gamma function that looks like a y. This is x, okay? So this is gamma of 1/2 plus 1 over 2 divided by 2 times, what is that? 2 times 1 to the 1 half plus 1 over 1 half, not over 2, over 1 half. Well, 1 raised to the crazy number, it's still going to be 1, agree? So this will be gamma of 1 half plus 1. Is that 3 halves? Is that 3 halves? Okay, so this is gamma of 3 halves over 1 half divided by 2. Okay, 3 halves divided by 1 half, is that gamma of 3? So this is gamma of 3 or 1 half gamma of 3, which is 1 half times 2 factorial, which is actually equal to 4. Well, hold on. Okay, this was supposed to be a 1 half here, which becomes a 2 there. Okay. All right, got it. And this is 2. This is 2, and that equals to 4. All right. Okay. All right, one more integral. Okay, one more integral, and we move on to calculating other multiples of gamma of a half. Okay, so for the integral from of x squared e to the negative 2x squared, what do we have? M equals to 2, a equals to 2, n equals to 2. All 2's here, all right? All 2's. So evaluating this would be gamma of 2 plus 1, right? Is that 2 plus 1 over 2, okay? Divided by 2 times 2 raised to the 2 plus 1 over 2, which will be gamma of 3 halves divided by 2 times 2 to the 3 halves, right? So 2 times 2 to the 3 halves. And what about the denominator? Power 1 plus power 3 halves. Combine the powers together. That is 2 to the 5 halves in the denominator, gamma of 3 halves in the numerator. But the question here is, how do we calculate gamma of 3 halves? Well, let's have a look at the exercises, at the next set of exercises, and then we're going to go back to this same one. All right. Okay, guys. So let's evaluate each of the following: gamma of 3 halves and gamma of 7 halves. All right, what are we going to need to compute gamma of? No, we're not going to evaluate the integral again. We're going to use the result we already have. So in order to get what we want to do here, we're going to rely on the following property or formula, if you will, on the fact that gamma of n plus 1 equals n gamma of n. All right? So this is what I'm going to do. I'm going to rewrite this gamma of 3 halves. Okay, gamma of 3 halves. Do you guys agree that this is gamma of 1 half plus 1? Is that equal to 3 halves? Now, does that look like the form n plus 1? What's n in this case? Do you guys agree this is 1 half? So this is gamma of 1 half times 1 half outside. All right? You guys see this? But what's gamma of a half? This is 1 half square root of pi, right? That's 1 half square root of pi. Then what's the next one? Gamma of 7 halves. For gamma of 7 halves, guys, we're going to take a few steps. So number one, I'm going to write gamma of 7 halves as gamma of, do you guys agree this is 5 halves plus 1? And then I'm going to use the definition. This n is going to be, so n, which is 5 halves times gamma of 5 halves. All right? So we're going to do this process in a recursive way, if you will. So we're going to take the iterations until we get to gamma of a half, and then write everything in terms of no gamma functions here. Okay, now at this point, 5 halves. Do you guys agree gamma of 5 halves is the same as saying uh, 3 halves plus 1? All right. Okay, so I'm going to use the definition again, this definition, and I'm going to write 5 halves times, I'm going to take out the 3 halves, times gamma of 3 halves. All right. And then I'm going to compute gamma of 3 halves. Although I already have it from part A. Well, let me do the whole process again. This will be 5 halves times 3 halves, gamma of, what is that? Uh, 1 half plus 1, which is 5 halves times 3 halves. And again, using the definition, I'm going to take this 1 half, write it in front of the gamma function times gamma of 1 half. So what's gamma of a half? If that's square root of pi, then let me multiply 5 times 3 times 1. Is that 15? Over 2 times 2 times 2, which is 8, square root of pi. All right. Okay, guys. Now here is the thing: can we find gamma or the gamma function for any value? Not every value. For practical purposes, we use the gamma function to relate factorials of integer values. And well, there is a way which I showed you to get a gamma of a half and multiples of a half. If you're wondering, is there a derivation for gamma of a third or gamma of a fourth? No, there is no derivation to date. I've been looking everywhere to see if there's something related, and I can't find. Although you can either look at tables of values or just a gamma function calculator online, but it's going to give you decimal. But the fun part, the interesting part, is to get these results with nice exact values, like in this case, the square root of pi, which is weird, isn't it? I mean, we are trying to find the gamma function of a fraction, which is related to the factorials. And in the end, we end up getting an irrational number. That doesn't make sense at all, right? That's just, I don't know, when I see these derivations, these results, I don't know what kind of sorcery is going on in there, right? It's so crazy in there, but I mean, it's mad. It's not how it works. I'm not making this up. I'm just, you know, Okay, guys, what about negative multiples of gamma? Okay, gamma of negative multiples of a half. Okay, guys, here's the thing. Let me evaluate one. Let me evaluate a couple. So again, what do we need? Let me write down what we need. Okay, so on the one hand, again, gamma of 1 half equals to square root of pi, and gamma of n plus 1 equals to n gamma of n. All right. However, remember how we use this in this direction? Now we're going to use this identity or this formula backwards. All right. We're going to do this backwards. We want to generate the left-hand side from the right-hand side. All right. Okay. So to evaluate gamma of a negative multiple of a half, we need to generate this guy first, all right? And I'm going to do the side trip first. So taking a side trip, negative 1 half. Okay, I need to generate this expression. All I need is an n, okay? What's n? Negative 1 half, all right? Okay, but what is equal to? Using the gamma function the reverse way, this is gamma of negative 1 half plus 1. All right? But what is negative 1 half plus 1? Isn't that plus 1 half? This is this is gamma of 1 half, gamma of negative 1 half times negative 1 half. But what's gamma of a half? Isn't that root of pi? And then multiply both sides by negative 2. All right? So gamma of negative 1 half equals to negative 2 root of pi. Okay? Negative 2 root of pi. So What about gamma of negative 3 halves? So on the next page. So again, well, let me first of all bring down these definitions here. I don't want to rewrite them again. Okay, so I need this over here. Okay, so let me take a side trip first. So I'm going to write gamma of negative 3 halves, okay? And I'm going to multiply by negative 3 halves. That is by the same number in the argument of the function, right? What does that mean? This means from here, I will generate gamma of negative 3 halves plus 1, all right? And well, what is negative 3 halves plus 1? Isn't that negative 1 half? Gamma of negative 1 half times negative, oh, this is 3 halves. Okay? But what's gamma of negative 1 half? Actually, didn't we compute it before? Didn't we compute that before? I'm just going to use the result from part A, which is negative 2 root of pi from A. All right? That's still equal to negative 3 halves gamma of negative 3 halves. Okay? And then I'm just going to multiply both sides by negative 2/3. Okay? And this will be gamma of negative 3 halves equal to negative and negative is positive. 2 times 2 equals 4 divided by 3 root of pi. Okay? So 4/3 root of pi. All right? Let me make this look like a root of pi. There we go. Hmm. In a similar way, guys, one more, and I think we should be good. Okay. Okay, let me do the gamma of negative 5 halves. Again, I'm going to do some side trip here. So gamma of negative 5 halves, but to generate the same definition again, let me actually bring it down here. I'm going to multiply by the number that's inside of the argument of the gamma function. So I can expound the definition gamma of n plus 1, where n equals negative 5 halves plus 1. And what's gamma? What's negative 5 halves plus 1? Isn't that negative 3 halves? We still have negative 5 halves, gamma of negative 5 halves over here. All right. So, but what's gamma of negative 3 halves? Well, I would have done another side trip just to get gamma of negative 3 halves. And in turn, I would have taken a second, or rather a third side trip to get gamma of negative a half. In this case, I'm just going to use the result from the previous exercises. All right. So from B, this is, what was that? 4/3, right? 4/3 gamma of pi equals gamma of negative 5 halves. That's halves, not fifths. Hmm. And then I'm going to multiply both sides by negative 2/5. All right. So that's going to give us gamma of negative 5 halves equals to negative this time. 2 times 4 is that 8. 5 times 3, that's 15 root of pi. All right. And of course, we can do the same to get, say, gamma of 17 halves, or gamma of 33 halves, or gamma of 101 halves. You would have to do this 100 and plus times. I mean, 50 something times rather, not 100. Yeah, not necessarily. Okay, guys. The next topic, it's actually formulas to compute this without doing this recursion. So it can be proved that we can simply use these formulas to identifying the value of it that it's involved, whether for a positive or negative power of a half, no, negative multiple or positive multiple of a half, we can use these formulas right here. However, I think I would like to skip these formulas. In the end, I already have video on my YouTube channel. We don't need to do this. This is just, like one of those curiosities or one of those extra pieces of information that I find interesting, but they're not that relevant. So I think I'm gonna stop here.